In this video, we're going further in circuit analysis, but let's revise what we learned in the last lesson first.
En el anterior vídeo aprendimos cómo calcular la resistencia equivalente de una red de resistencias. Calcular la resistencia equivalente no es otra cosa que encontrar el valor de una única resistencia que se comportaría como toda la red de resistencias a la que equivale. Esto, que puede parecer extraño a primera vista, es fundamental a la hora de analizar circuitos. Lo veremos más adelante. Para un grupo de resistencias que están conectadas en serie, lo único que hay que hacer es sumarlas, así de sencillo. Si están conectadas en paralelo, la resistencia equivalente se calcula con esta fórmula, que para dos resistencias se puede escribir así. Os recomiendo que cuando las resistencias estén conectadas en paralelo, siempre calculéis la resistencia equivalente cogiéndolas de dos en dos, porque los cálculos serán siempre más sencillos. Además, si las dos resistencias tienen el mismo valor, habréis comprobado ya que su equivalente siempre resulta ser la mitad. Finalmente, os propuse una actividad con ejercicios para que practicaseis el cálculo de resistencia equivalente. Voy a resolver rápidamente algún ejemplo. Voy a empezar con este de aquí. Y es importante tener claro el orden en el que vas a reducir la red de resistencias. No se puede hacer el equivalente en serie de R1 y R3, por ejemplo, porque lo primero que hay que hacer es R1 y R2 que están en paralelo, y entonces el circuito que me va a quedar es esta resistencia, que será el equivalente de R1 y R2. Ahora calcularé lo que vale en serie con R3, que es 50 ohmios. El paralelo de R1 y R2, pues ya sabéis que se calcula mediante esta formulita. Solo vale para grupos de dos resistencias. Eso tiene que dar 25 ohmios. Y eso son 25 ohmios. Y ahora tengo dos resistencias en serie y la resistencia equivalente total, digamos, va a ser la suma de 25 más 50, 75 ohmios. En el siguiente caso, pues tenemos un paralelo de dos resistencias aquí y otro paralelo. Y esto se va a resolver pues calculando primero el paralelo de este y de esta. Y tenemos la resistencia equivalente aquí voy a llamarla R1, 2. Y en serie estará R3, 4. Se calcula muy fácil y luego la equivalente de estas dos en serie, ¿vale? Esa resistencia equivalente, pues ya sabéis que será la suma de R1, 2 y R3, 4. Este otro circuito de aquí, pues tenemos R1 y R2 en serie aquí y R3 y R4 en serie aquí. Y que para calcular resistencia equivalente total, primero calculamos en serie R1 y R2 y luego R3 y R4 y quedaría un circuito R1, 2 aquí y en paralelo R3, 4. Estas serían la suma. R1, 2 pues sería 30 ohmios y R3, 4 sería 100 ohmios, 50 más 50. Y aquí pues sí que habría que calcularlo con la formulita para obtener la resistencia equivalente final o total, como la queráis llamar. Este último de aquí, pues hay que calcular primero, todas las resistencias son de 10 ohmios, habrá que calcular primero la equivalente a R2 y R3 en serie. Entonces, pues esto sería sumarlas y nos quedaría un circuito equivalente intermedio, digamos, con esta configuración de aquí, donde aquí estaría R1, que seguiría valiendo 10 ohmios, esto sería R23, que sería 20 ohmios, R1 es 10 todavía, y R4 aquí abajo sería 10 ohmios. Y luego pues habría que seguir calculando a pares las resistencias equivalentes en paralelo hasta llegar a una sola resistencia equivalente.
Circuit analysis is about finding the unknown currents and voltages in a circuit.
And now that we know how to calculate equivalent resistances, we are ready to learn the basics of circuit analysis.
Most times, we will need to find different voltages and electrical currents in the circuit. We will learn how to do this in different circuit configurations.
When we analyze a circuit in series like this one, we will only have one electrical current flowing through all the circuit. This electrical current will cause voltage drops across every resistor, like V1, V2, and V3 here. If we add them up, we will obtain the value of the voltage source, in this case is 6 volts. These three voltage drops and the electrical current is what we will have to calculate. And don't worry if you're a bit confused right now, I'll show you how to do it. Okay, so first thing you need to think when you are trying to analyze a circuit is the things that you need to calculate. What you need to calculate here is the electrical current flowing through the circuit and all the voltage drops in the circuit. It's going to be a voltage drop here, another voltage drop across resistor 2, and another voltage drop here. All right, so these four things is what we have to calculate in this case. Well, how do we start? We have to apply Ohm's law. As you know, Ohm's law is this one, but we have to apply that to every resistor. So we can calculate the voltage drop across this resistor. We will need to know the electrical current flowing through the circuit. So as we don't know the electrical current yet, we cannot calculate that voltage drop. What do we do? Okay, in this case, as the circuit is in series, what we're going to do is to calculate the equivalent resistance of these three resistors. So it will be something like this. I'm going to redraw the circuit. The battery is going to be the same here, but instead of three resistors, I only have one now. This is my battery. It is still 6 volts, and this equivalent resistor, as they are in series, is just adding them up. 50 plus 20 plus 50 is going to be 120 ohms. Okay, why do we do this? Because now we know what is exactly the voltage drop across this resistor. As the battery is here, we will say that the voltage at this point is 0 and the voltage at this point is 6 volts. This is not completely true, but for circuit analysis, we're just going to go with it. Every time we know the voltage at a point in the circuit, like this one, this voltage here is 6 volts. Every time there is only a conductor, we can tell that the voltage here is the same exactly. There are 6 volts here too, because between these 2 points, there is only a conductor. There are no resistors or anything like that. So the same we can say here. At this point, the voltage is 0, and all through this path, there is nothing but a cable or a wire, a conductor. So there are no voltage drops here. We can tell that the voltage at this point is 0 too. So the voltage drop across this equivalent resistor has to be 6 volts. Okay, why do we want this? Because now we can calculate the current going through this resistor, applying Ohm's law. There it is. This is the voltage drop. Here it is 6 volts. And the resistance is 120. Okay, so this should be 0.05 amps, right? Now, why did we do all this? Because it happens that this electrical current that we just calculated is the same electrical current that we have up here. Now we know that this electrical current here is 0.05 amps. Now we already know something. We know that the electrical current in our circuit is that. What can we do next? Well, we can apply Ohm's law to every resistor to find out what is the voltage drop across them. Let's do that. I'm going to move down here. Okay, right here. Let's find what is the voltage drop across resistor number 1, V1. I am applying Ohm's law again, and it's 0.05 multiplied by 50. That is going to be something like 2.5 volts. The voltage drop across the second resistor. The same thing, current intensity, but this time resistor 2, 0.0520. This is going to be 1 volt. And the voltage drop across resistor number 3, we can calculate it the same way. This one is 50, and as it is the same numbers, we know it's going to be 2.5 volts. But even if we didn't calculate it, we could know, because the voltage drop across resistor 1 is 2.5 volts. Through the second one is 1 volt, and the battery has a value of 6 volts. So this one has to be 2.5 again. So the 3 voltage drops will add up to 6 volts. Okay, so that's how you do it. When analyzing a circuit that is in parallel, what you need to remember is that every resistor is connected directly to the battery, so the voltage drop will be the same at every resistor. We will have a different electrical current through every branch of the circuit, and we can calculate the total electrical current of the circuit by adding them up. Let's see how to do it. Okay, so to solve a parallel circuit, again, what we're going to think is, what do I have to calculate here? And again, it's all the electrical currents in the circuit and all the voltage drops across every resistor. Now, how many different electrical currents do we have in this circuit? There is an electrical current, a flow of electrons that is starting here and gets up to this point. And then this current, I'm going to call this just I, and then this current will split into 3 different electrical currents. First one is going to go through this resistor. I'm going to call it I1. We were going to have another current going through this resistor too. I'm going to call it I2, and another electrical current flowing through resistor 3. That is going to be I3. So we have 4 electrical currents. What about the voltage drops? Well, there are 3 resistors, so we have to calculate 3 voltage drops. I'm going to call them V1 here, which will be V2 and V3. This voltage drop is the voltage drop from this point to this point. V2 would be from this point to this point. Voltage drop 3 will be from this point to this point. If this is sounding complicated to you, don't worry, because it is easier actually than the serious one. Let's start with the battery. I like to start with the battery always. What is the voltage at this point here? Just right below the battery. Well, the voltage there, we always say it's 0. And as the battery is 6 volts, we will say that the volts that we have here is 6. Again, there is no resistors through this path. There is only a conductor. So what is the voltage going to be at this point? It's going to be 6 again. And what about this point? It's 6 again. And this point here, it's 6 volts again. Maybe some of you are thinking, wait, but I thought that electrical current was splitting in 3 different currents. Yes, that is true, but that doesn't apply to voltage. Voltage will remain being the same, even if there are different branches in the circuit. Like if I wanted to connect a wire here and take the wire over here and spin it around and then go down here, the voltage at this point would be, guess what? 6 volts. But okay, so I'm going to keep thinking about voltages. The voltage here is 0 volts. I only have a wire here, so what is the voltage here? Yes, the voltage here is 0. And at this point, again, the voltage is 0. And at this point, yes, it's 0 again. So what is the voltage drop from this point to this point? What is V1? 6 volts here, 0 volts here. The voltage drop here is 6 volts. And the voltage here is 6, 0 here. The voltage drop at resistor number 2 is 6 volts again. And the voltage drop at resistor 3 is 6 volts again. So they are all the same. They are all 6 volts. We already calculated all the voltages in the circuit. This will happen every time we are analyzing a parallel circuit, because they are connected in parallel. They are directly connected to the battery. So the voltage drop in every resistor is 6 volts. Now, the electrical currents. Let's think about how to solve this. Some of you may be thinking, okay, I know how to do this. I can calculate the the equivalent resistance of these 3. I know I have to calculate first 2 of them, and then I will find only one equivalent resistor. Well, you could do that, but that is more work than you need. Instead of that, what you're going to do is to apply Ohm's law to every resistor. And what I mean is, let's take, for instance, resistor number 1. We know that the voltage drop here is 6 volts, and we know that the resistance is 50 ohms. So we can apply Ohm's law to calculate the electrical current through resistor number 1. Voltage drop number 1, resistor number 1, voltage drop is 6, 50 ohms, and I need a calculator for this. I2, voltage drop 2, R2, 6 volts again, this time is 20. I will do the numbers later. And I3, it's going to be the same as I1, but I'm going to write it anyway. It's 6 volts and it's 50 again. Okay, so when we do the numbers, you'll see that if we add them all, we can calculate the current intensity flowing. This current intensity will be the result of adding the three of them here. I don't know if that is quite clear. I think it is. That's how you do it.
We will often find circuits that are not exclusively connected in series or parallel. These mixed circuits are a bit more complex to solve, but the same concepts apply.
When analyzing a mixed circuit like this one, we will have to calculate the voltage drop at every resistor, but also the different electrical currents flowing through the circuit. Let's see how to do it. So this is a mixed circuit, and it's a bit more complicated than the previous ones, but it's not that hard either, and the same concepts apply. First thing I want you to think is, what do I have to calculate? Well, you have to calculate the electrical currents in the circuit. There is an electrical current that flows through here, and it splits at this point. It will split into this one and also this one. I'm going to call this current I1 just because it goes through resistor number 1. This current, I'm going to call it I2, and this one is going to be I3. We have to calculate these three, and also every voltage drop in the circuit. That means we will have to calculate this voltage drop here, V1, and also the voltage drop here, V2, and the voltage drop here, V3. V1 being the voltage drop from this point to this point, V2 the voltage drop from this point to this point, the same for this one. Okay, so it's going to be 3 electrical currents and 3 voltage drops. Now, where do we start here? I always like to start at the battery. I'm thinking about the voltages. A battery, it creates a difference of potential energy between these 2 points, here and here. And we always say this one here is the cold, it's 0 volts, and here it's 6 because it's the value of the battery. If this battery was 12 volts, this voltage here would be 12. If we follow the wire, no resistors here, there are 6 volts here. Okay, that's what we know. And if we follow this wire through this path, there are 0 volts here and 0 volts here. Well, that is not helping a lot because now we don't know the voltage here or here. We are stuck here. What do we do? Well, in this case, we are going to have to calculate the equivalent resistance of these two and then reduce the whole circuit to only one resistor. So I'm going to do this in steps. I'm going to redraw the circuit. I'm leaving resistance number 1 there, but these two now are going to be this resistor here. So I have to calculate the parallel of those two. This is still R1, 50 ohms, but this is now R23. Parallel of these two, 20 multiplied by 50, 20 plus 50. I did the numbers beforehand this time, and that is 14.29. 14.29 ohms. All right, I am not done yet because I want to have only one resistor. So now I will have to calculate the equivalent of these two that are in series. I mean these two. And I'm going to redraw the circuit again. This is the same battery, which is 6 volts, and this equivalent resistance is now just adding 50 plus 14.29, so it's 64.29 ohms. Why are we doing all this? Okay, now I can calculate the intensity, the current intensity flowing through this equivalent resistor, applying Ohm's law. So it's the voltage drop, which is 6 volts are dropping across this resistor. 6 divided by 64.29. And if you use a calculator for that, you will find that current intensity is 0.0933 amps. When the electrical currents are so small, I recommend you to express them in milliamps. So that would be 93.3 milliamps. By the way, to convert this number in amps into milliamps, you only have to multiply by 1000. It's like millimeters and meters. All right, so we did a lot of things. But what was all this for? Well, now we know something else. We know that this current that we just calculated here is this one. Maybe you're wondering, okay, why this one? Because we just calculated the electrical current flowing through the equivalent circuit that only had one resistor. So that current that we just calculated is the biggest one in the circuit. And the biggest current in this circuit is I1, this one here. This is 93.3 milliamps. Okay, we already calculated that. So what can we do next? Well, now that we know the electrical current flowing through resistor number 1, we can calculate the voltage drop across resistor number 1. And to do that, we need to use Ohm's law again. I'm going to do it here. Voltage drop across resistor number 1. This is I1 multiplied by R1. Be careful here because you have to write the current intensity in amps, not milliamps. Careful. The value of the resistor is 50 ohms. And again, if you calculate that, you will find that voltage is 4.67 volts. Please never forget the units. Okay, there is another thing that we calculated. Now what? Okay, pay attention here. This is the voltage drop at resistor number 1, this resistor. And we already know that the voltage here is 6 volts. And at resistor 1, we are losing, there are 4.767 volts that are falling. So the voltage here will be 6 minus 4.767. That gives us a voltage at this point of 1.33 volts. Okay, so if we have 1.33 volts here, we have the same voltage here. We also have 1.33 volts here and also here, as you already know. So now, what is the voltage drop in resistor number 2? If we have 1.33 volts here and 0 here, the voltage drop is 1.33 volts. The same applies to resistor number 3. So we already know that. But I'm going to write it down here. Voltage 2, which is equal to voltage 3, is 1.33 volts. 1.33 volts. So we are almost done. What's left for us to calculate here? Well, if you take a look at the circuit here, we didn't calculate this electrical current I2 and this electrical current I3. We don't know them yet, but we know the voltage drop across resistor 2 and the voltage drop across resistor 3, so we can apply Ohm's law again. And I'm gonna do it. Yeah, I'm gonna do it here. I think that will be okay. I'm going to separate this. So I2 is voltage drop 2 divided by resistor 2. Voltage drop is 1.33 divided by 20 ohms. And that will give you a number like 0.0665 amps, which will be 66.5 milliamps. For current, electrical current 3, same thing, same voltage here, but the value of the resistor is 50, and that will give you a current of 0.0266 amps. Okay, so that will be 26.6 milliamps. And now we have everything. It's easier than it looks. It takes a little bit to get used to understand how these circuits work, but if you practice a little bit, you'll get through it.
Let's practice a little bit. Find all the electrical currents and voltage drops in every circuit.
Y bueno, ahora lo que te propongo es que trates tú de resolver los 3 ejemplos que he resuelto en este vídeo. Intenta hacerlo sin mirarlo primero, y si no te sale, miras la solución hasta que comprendas cómo se resuelve cada tipo de circuito, tanto el serie, el paralelo y el circuito mixto. Y después intenta hacer los demás, porque se resuelven siguiendo la misma estrategia. Buena suerte.